happy to have Stephen Prohira from Ohio State University for the NPA seminar. So Stephen is a presidential postdoc fellow at the Center for Cosmology and Astroparticle Physics at the Ohio State University. Stephen is the PI of the Radar Echo Telescope, or RET, and he did grad school at Kansas University under the supervision of Professor Dave Bessa, working on radio detection of neutrinos. I think Stephen, among other things, he did some analysis for the Anita experiment, which I'm sure people here have heard. And so Stephen has some field work around the world. I think, Stephen, you've been several times to Antarctica, right?
Twice so far.
Twice to Antarctica. And so Stephen and I worked together on the T576 experiment that Stephen will talk about in this talk. And yeah, I think, Stephen, just take it away.
Okay, thanks a lot, Jorge. I appreciate the introduction, and thanks for the invitation as well. So I'm really excited to talk to you about prospects for detecting ultra-high energy neutrinos using a new experiment called the Radar Echo Telescope. And on the slide here, the names of my collaborators in our small collaboration, and this work is also presented on their behalf. So also throughout this talk, if you have questions, feel free to jump in or save them till the end, whatever's most convenient for you. All right, so the outline of my talk is here. I'm going to give a little bit of an invitation to why this problem I think is interesting, what the motivation is for my own research program, some experimental work that we've done, and then the outlook for the future of this particular technology. And so we'll jump right in with what is interesting about neutrinos and ultra-high energy neutrinos specifically. So you may have seen several versions of this cartoon before. One interesting thing about neutrinos as cosmic messengers is is that they can point back to their origins in ways that other messengers can't. So cosmic rays, charged particles are going to be bent on their path from source to Earth. Photons can downscatter, but neutrinos can really pass unimpeded from source to receiver, and that makes them very, very compelling cosmic messengers if you're trying to elucidate what the sources are. From a more particle standpoint, which is kind of where I stand, they're fascinating because they're the only observed particle that we've seen with beyond standard model properties. So they have mass, and they shouldn't. They oscillate between flavors, which is quite weird. They only interact via the weak force. They're less than 10 to the 6 times the mass of the electron. So I'm not going to talk about any of that in this talk, but neutrinos themselves are interesting and we want to study them further. Moreover, the ultra-high energy regime, as I mentioned before, they can point back to sources. Well, what's interesting about that is that the sources of these neutrinos and ultra-high energy cosmic rays, which I'll talk about a bit in this talk as well, is not known. And the interaction cross-section, this figure on the left shows the neutrino nucleon charge current cross-section as a function of neutrino energy. That cross-section is not constrained at very high energies. And furthermore, these UHE neutrinos, when they interact and produce an interaction, that interaction occurs at a center of mass energy that we can't access on Earth, that we can't access at terrestrial colliders. So there's a lot of interest in why we'd want to study these things, but maybe the most simple reason we want to study these things is simply because they're there, okay? So what I show on this figure is a plot of the measured cosmic ray spectra by various experiments. So the y-axis is the flux. This has been scaled to make it a little bit easier to read. And then on the x-axis is the energy. And ultra-high energy cosmic rays, so charged particles, nuclei, even protons up to iron nuclei, for example, they've been detected at Earth with energies above 10 to the 20 electron volts. But the highest energy neutrino that's been detected to date is several orders of magnitude lower. But we know that ultra-high energy neutrinos are produced via interactions with cosmic rays and the cosmic microwave background. So we know that there should be neutrinos at those energies. So they're there just waiting for us to detect them. So why haven't we seen any if they're there? The reason is twofold. One is there's an extremely low flux and the extremely small interaction cross section. So the highest energy neutrinos detected to date are around 10 PeV. So the lack of observation of neutrinos with energy greater than that. Sorry, is everyone still seeing my screen?
Yeah, we can say it.
Okay, sorry, I just got like a weird blip. Thanks. So the lack of observation of neutrinos above 10 PeV suggests that their flux is perhaps as low as 1 per square kilometer per steradian per decade at these energies. So it's a very, very small flux. So in order to detect something that small, you have two options. One is to scale up your detector, which is very, very expensive. And the other is to just wait a long, long time, which is extremely boring. So luckily there's a third option, and that third option is to develop a new technology that can instrument a much larger volume much more efficiently. Because we don't want to just detect UHE neutrinos, we want to study them. And for that, we need some statistics. So how do you detect a neutrino? So you can't actually detect a neutrino. You can't measure the neutrino itself at these energies. What you can detect is a subsequent cascade that's produced by the neutrino. So on the right-hand side of this plot, you see an example cascade. So a neutrino is coming in, for example, and this is ice. Neutrino comes in and it interacts with a water ice molecule, and it produces this cascade of secondary particles. If that cascade occurs in a region that your detector is sensitive to, you can detect it. And there are various strategies to do that, and I'll go through them quickly before I get to the radar method. So the most successful technology for detecting neutrinos so far, neutrinos with significant energies, is optical detection. So when one of those cascades occurs in ice, for example, the cascade particles are actually moving superluminally. They're moving faster than the speed of light in ice. And that produces Cherenkov light. And that Cherenkov light can be detected by optical modules. So what I'm showing here is the ice cube experiment, cubic kilometer detector at the South Pole. It has thousands of these optical modules. And on the right is a reconstruction of one of their events. So you have a neutrino that comes in and it produces a cascade. That cascade occurs in the volume and it produces ice, or produces light in the ice, and they can pick that up. And they've successfully detected neutrinos up to 10 PeV using this technology. At the ultra high energy regime, so energies in excess of 10 to the 17 electron volts, you can't really detect things with light anymore in the ice. And the reason for that is it scatters. And so it gets attenuated, it gets scattered, and so you can't see it beyond some horizon. But what's interesting is that ice is largely radio transparent. And so there's a similar effect that occurs when a cascade is moving superluminally through the ice. You actually get this incoherent Cherenkov light, but you also get a coherent radio signal. Radio meaning, radio waves that have meter scale wavelengths. And these radio waves can proceed through the ice largely unimpeded. So there are several experimental strategies at very high energies. Now they've not seen a neutrino signal yet, largely because of this low flux, but there are several strategies both in ice and in air. Here I show a picture of the Anita experiment.
I just have a real quick question. Can you state why again that the ultra high neutrinos you can't see the optical signal from the cascade? You say why that is again?
The main reason is you're limited by the horizon distance. So the attenuation length of an optical signal in ice, meaning attenuation length being, it's a measurement that's like the distance over which the amplitude of the signal falls is 1/e. That's like order 100 meters for optical, and it's more like a kilometer for radio. And what that means is that you need to have your detectors spaced with a distance commensurate to that attenuation length. So if you wanted to detect a much higher energy cascade with ice cube, you'd need to make your detector a lot larger because the flux is much, much smaller. So the flux goes as something like e to the minus 2.5. So you'd need to make your detector much, much larger in order to have a chance of seeing one of these things, essentially. So you need something that can instrument a larger volume more sparsely than the optical technique. And radio allows for that. So hopefully I've answered your question.
You just need a really big detector, but you could still see it.
Right. You could still see it. You would just need a huge detector because you need to instrument it on a much smaller spacing. That's a good question. So instruments here, like this big crazy looking wedding cake kind of Mad Maxy thing. This actually hangs from the bottom of a balloon the size of a football stadium, floats over Antarctica and listens for radio impulses from the ice when these neutrinos interact. And what's cool about that is that it can instrument a massive, massive volume all at once and increase the target volume to something that you could maybe try to see something at these extreme energies. Now, this signal hasn't been observed there, but lots and lots of experiments, some of which I've listed here, have been showing, have been trying. So the large picture, and this is not exhaustive, is that there have been observed neutrinos up to about 10 PeV, 10 to the 16 electron volts. There's lots of technologies for very, very high energy neutrinos, and there's something of an energy gap kind of in the middle here. And we think that that energy gap can be filled with the radar echo method. And so that's what I'm going to talk about for the rest of this talk. So the motivation for my particular research program is, can we use radar to detect ultra energy neutrinos in the ice and sort of try to push the energy scale up beyond what's possible with optical detectors. So you need two concepts that are both very simple in order to understand the radar echo method. So we're going to go back to the idea of a particle cascade. Neutrino comes in, makes a cascade. So here we have a neutrino coming in from the left. It interacts with a water ice molecule, and it produces this superluminal cascade that I talked about earlier, this cascade of particles that's moving faster than the speed of light. But now we're going to focus on something different, which is what's left behind as that cascade moves through. And that's a cloud of ionization, because those cascade particles are basically losing all of their energy to ionization. So you get this little short-lived ionization deposit that trails behind the cascade front. And so that ionization deposit is one concept that you need to keep in mind. The other concept is radar, and that's exactly what you think it is. So you have a transmitter that's broadcasting radio into some volume. If a conductive surface lives inside of that volume, it'll reflect that radio to a receiver that's also monitoring the same volume. So the big picture concept is to bounce radio waves off of the ionization deposit that's left in the wake of the neutrino-induced cascade. So that's the radar echo method. So this is not new at all. I didn't come up with it. It was like the first thing that people thought of when they first invented radar back in like 1940, 1941 during World War II. There were these weird radio reflections that were coming from the upper atmosphere, and nobody knew what they were. And Pierre Auger had just recently developed the theory of the extensive air shower, which is when a cosmic ray comes into the atmosphere, interacts in the upper atmosphere, and produces this huge cascade of particles similar to the neutrino-induced cascade, but on length scales of tens of kilometers. And so they thought maybe what they were seeing in the atmosphere were reflections from cosmic rays. And so they built the Jodrell Bank Observatory actually to try to detect cosmic rays in this way. Turned out it doesn't work. It was meteors that they were detecting the whole time, but the idea sort of stuck around. And I'll briefly mention radar detection of meteors because it's quite intuitive. So a meteor comes into the atmosphere, and it'll produce an ionized trail through the atmosphere. And if they're really big, and by really big, I mean like a grain of sand, you can see this with your eyes, and that's a shooting star. If they're smaller though, and you can't even see them, there's still a very appreciable ionization deposit, and you can actually bounce radio off of this. So this was actually the way that they would transmit radio signals beyond the line of sight before satellites were invented, is you just be broadcasting your radio signal, and then eventually a meteor would come by and boop, it get bounced to wherever you want it to go. So what you see here is a spectrogram. There's frequency on the y-axis and time on the x-axis, and you see this little blob. So what's going on here is there's this, as the meteor is moving through, it has some velocity, and the ionization that it carries with it reflects radio, and that produces a Doppler shift. So you get this nice Doppler shifted signal. But then the trail of the ionization that's left behind is stationary, and it persists for some amount of time. And that will also reflect radio, and that's this sort of monochromatic tail signal. And these time scales are much, much longer than what we're looking at with neutrinos. But the basic principle of reflecting radio from something that's moving and something that's stationary is very, very similar. So in the early 2000s, this sort of idea was revived to see if you could detect cosmic rays using radar, because now we have bigger antennas, better receiver technology. Let's try it again. So the telescope array radar experiment went out to Utah, and they co-located a bistatic radar system, meaning transmitters over here and receivers over here, with the telescope array cosmic ray detector surface system. And the idea was that if a cosmic ray occurs and the surface system measures it, we can look and see if we saw a radar reflection from it. The transmitter was massive. It was 40 kilowatts, so like a typical FM transmitter station. And that's this call sign over here, this WF2XHR. And this is the approximate illuminated volume, and each little dot on this screen is one of the surface detectors for the telescope array. So this didn't work. I ran for a long time. They reported no signal. And that is because of a couple of factors. The ionization densities just don't get high enough in air for two reasons. One, the free electron lifetime is very short. There's a plot of this on the bottom left here, where the tau, the average lifetime, mean lifetime of a free electron, is given as a function of altitude. So you can see that they last for tens of nanoseconds, so not very, very long. So a free electron will be produced by the cascade as it moves through, and then it'll get gobbled back up a few nanoseconds later. And also, it doesn't just get gobbled back up, it gets bounced around and hits all sorts of stuff as it lives, and that reduces the efficiency of its ability to re-radiate incident radio. And so these two effects combined make it so that you can't really detect cosmic rays using radar in the air. But what about in the ice? So the density of ice is 1,000 times higher than air. So the cascade is about 10 meters long, therefore, instead of 10 kilometers. So you get this many, many orders of magnitude increase in the ionization density. So you still have short plasma lifetimes and you still have collisions, but it's offset by this massive increase in the density of the density of the ionization. And so it occurred to some people in around 2013 that we could maybe detect neutrinos in ice using this, even if it doesn't work for cosmic rays in the air. And on the bottom here, I just have a plot of the plasma lifetime in ice. And here it's actually time on the x-axis, conductivity on the y-axis. But basically, if you look at some of these things like this curve for minus 40 degrees Celsius, you can see that the lifetime is order a few nanoseconds, which is similar to air. So a lot of things are quite similar here, except we have a much higher ionization density. So then the idea was, let's try to model it. So there's some macroscopic models that exist to try to describe this, this phenomenon. It's a little bit challenging because of the time scales and length scales involved. You have something that's moving relativistically over a very short time length. And so an alternative approach to developing some sort of macroscopic model is to kind of outsource a lot of the cascade physics, the hard stuff, to people that know what they're doing. So Geant 4, which many of you are familiar with, is a beautiful simulation suite to basically slam any particle into any object made of any material and see what happens. So you can create a cascade and then scatter radio off of that cascade. And so we built this into a module called Radio Scatter. And I'm just going to talk briefly about it. I don't like showing giant equations on a slide during a talk. So I'm not going to go through the whole thing. I'm just going to draw your attention to a few things to sort of develop an intuitive picture of how this scattering happens. So there's a little cartoon here. You've got a single charge labeled A, and you have a transmitter here at the origin, and then you have a receiver over here some distance away. And we want to figure out what the scattered field is from that individual ionization electron. So we have some prefactor that doesn't really matter. We have some geometric terms that also don't really matter. And then this EI is the incident field. So remember, we have a transmitter and we're transmitting radio, and then it's got to bounce off of something and reflect to a receiver. So we have some control over our incident electric field. Then there's a couple quantities of interest over here. One is what's called the plasma frequency. So the plasma frequency is largely a proxy for the number density of the cascade. And so it's something of a measurement of how well your radio scatters from a cascade of some density. Then a couple other quantities here. Omega is the actual broadcast frequency, the transmitting frequency of your radio. And then this nu C is the collisional frequency that I was talking about earlier. So you can see that there's this kind of complex interplay between the density of the cascade, the collisional frequency of the cascade, and the interrogating frequency of your radio. And those all sort of combine to produce a rather complex time domain structure to the signal that you're looking at. But basically, you can calculate this from first principles and then just sum up the contribution from all of the individual cascade particles and see what happens. And what turns out is you get quite nice signals from something like this, even with ionization lifetimes as short as 1 nanosecond, including all of these collisional effects that were really damaging for the in-air prospects. So what I have here is an example of a signal from something like a beam test. So this is where we have a 10 GeV electron beam that's going into some sort of dense material, and we're interrogating it with a 100-watt transmitter at a baseline of maybe 100 meters. And we can see that we get a pulse of a few millivolts that has some nice distinct structure to it. And so this was quite interesting because it, putting in all the things that killed the in-air process really don't seem to affect it in ice. So this led us to trying to see if we can, test it out in the lab. So the idea behind this is quite simple. Ice is really annoying to get a big block of and keep it cold. So you can go and get some plastic that's a lot easier to work with and has very similar radio properties to ice. So we got this high density polyethylene target. And then we go to SLAC, National Accelerator Laboratory, where they have a beam pipe that can spit out electron beam. And we create a cascade in that material. And then this is now looking from above. You interrogate that target with radio. And then when that cascade happens in the target, you should see some signal in your receivers. So we went out to N Station A at SLAC. And this is sort of not part of the main linear accelerator out at SLAC, but it's this massive room that has a very storied history. Lots of experiments have been done in this room. And you basically have access to their full beam. It's each electron has about 10 GeV, and there's about 1 billion electrons in a bunch. That's very, very tightly collimated. And you can set up your experiment. So what we have here is the beam pipe. Hopefully you can see my cursor here on the left. The beam comes out of that through a little bit of air and then slams into this large plastic target. Around that target, we situated a bunch of receiving antennas. These are some wideband log periodic dipole antennas and our electronics. And this was experiment 570, test beam experiment 576, T576. And you may recognize Jorge, who was an integral part of the first run that we did. We did 2 runs during 2018. We went there, we saw a hint of a signal, then we went back and fine-tuned things a little bit more for a second run. And we were able to see a signal. So what we have here is another spectrogram. You have frequency on the y-axis and time on the x-axis. And we have this null data here, which is essentially a sum of all of our backgrounds, radio backgrounds, and then our data. And you can see that there's this very clear excess at the expected return radar frequency with a duration of a few nanoseconds that's fairly consistent with simulations. So this was the first ever observation of this signal, a radar detection from a cascade. And we got a little bit of press about this a couple years ago, and you can check that out if you're interested in more details. So it was a lot of fun. It was an interesting experiment. We saw a signal, and so the next obvious idea is to go test it out in nature. So let's say that you go out to an ice sheet, you put a radar system out there in the ice, and you see a blip that could be from a neutrino. Well, prove it. How do you prove that what you see is what you think you're seeing, especially when these signals are going to be extremely rare? And so our idea was, instead of jumping straight to detecting neutrinos, we're going to try to detect cosmic rays. Now, I know I told you that doesn't work, but it can work in the ice. So let me tell you how. So when you have a very high energy cosmic ray, so something like greater than 10 to the 15, 10 to the 16 electron volts, and you go out to some place where the ground elevation is quite high, a significant fraction of that primary particle energy will hit the ground. And that fraction gets larger the higher the ground is, of course, because you're sort of truncating the cascade. The East Antarctic ice sheet is about 2 to 3 kilometers in elevation. So what you can do is you can go out there and try to look for the in-ice cascade that's produced when a cosmic ray air shower hits the ice. And what's interesting about this, and it was, before we looked at this, I wouldn't have believed it, but we ran lots of simulations, that in-ice component is very, very tightly collimated. So it's almost all within a few centimeters of the cascade axis. So you get this very dense cascade at the very top of the ice that contains a lot of the energy of the primary cascade. And so what you can do is you can put some charged particle detectors on the surface that will trigger when a cosmic ray comes through and tell your radar system to take a snapshot. So you've got your transmitter and your receiver in the ground, in the ice, and you try to detect this very dense in-ice portion of the cascade. So we proposed this to NSF, and we got a little bit of funding, and we call it the Radar Echo Telescope for Cosmic Rays. And the layout for this experiment is shown here on the right. So in the middle, we have this inset is sort of what's going on right here in the center. We have a phase transmitter array that I'll talk about in just a second. We have a data acquisition system. We have our amps, and it's all autonomous on solar power. And then these 8 dots in black that you can see here on the diagonals are our receiving antennas. And then we have the cosmic ray detectors, as I mentioned, on the surface. And this surface system serves as our trigger because we know that there's charged particles in the cascade. We know that they're going to hit the ice. And so our surface system can form our trigger, and then we can use that to test actual radar triggers in the ice. So you take a snapshot, and then you have a trigger that's running on, for example, the integrated power of the radar signal that's coming back. And you can test whether or not that particular event would have triggered in your detector. So we can use this as a test bed for when we eventually turn our sights to neutrinos. So this curve here on the left is the trigger efficiency of the cosmic ray system, or surface system, excuse me. So you can see that it's tuned so that it's very inefficient at 10 to the 15 electron volts. And that's because the rate of 10 to the 15 electron volt cascades through our surface here is actually quite large. We wouldn't want that to swamp our detector. But we do want it to be very, very efficient at the energies for which we can expect a radar echo. and that's above about 10 to the 16.5 electron volts. So we have full efficiency, simulated of course, full efficiency at that energy. The other interesting thing that we're trying to do is use a phase transmitter array. So we put 8 antennas down a borehole, and then we feed them individually and phase their outputs such that we can point the beam where we want it to be. I'll talk a little bit more about ice properties shortly, but there's an interesting feature in the ice where when you send out radio waves, they don't move straight. They bend in the ice because there's a non-uniform density, a non-uniform index of refraction in the ice. So we can actually use our phase transmitter to steer our beam and keep all of that power right near the surface. Because remember, we only expect these cascades for the cosmic ray experiment to occur just beneath the surface of the ice. So we expect a signal that looks something like this. So this is a 10 to the 16.5 electron volt cascade that's occurred within the volume. Let me see, do I have, yep. So I'll talk a little bit about the way that we simulated this in just a moment. But you can see that we have this sort of same characteristic frequency shift that I showed on a plot much, much earlier. And what's cool about this is that based on your geometry of your transmitter and cascade and receiver, you get different frequency shifts of your return signal. And what that means is you have a handle on angular reconstruction just based on the properties of the signal that you receive. And so we're really, really interested to study this in nature and see if we can actually, well, first we need to see if we can detect it at all. And then we want to study it to see if we can use it in our trigger routines for an eventual neutrino detector. So we calculated our event rate for RET-CR, and we did this using a 3-part simulation chain. So we had some folks at Vrije University Brussels, Rose Stanley and Katie Mulry. They produced some cascades using Corsica, so cosmic ray cascades using Corsica, and they propagate those through the atmosphere. And then they take the charged particle content at the surface, and we use that as the input to JOUnt4. Then we produce cascades inside of the ice using JOUnt4. Then we plug that into radio scatter and see what the radar signal is off of those in-ice cascades. And so using this sort of 3-step process, we come up with an event rate that's shown on this slide. So let me tell you how to read these figures. Basically, this is the event rate as a function of the trigger signal, or the signal to noise ratio at our detector. So it ranges from -10 dB relative to thermal noise to +3 dB relative to thermal noise. And so these are kind of the bands of what we can expect to detect based on how sensitive our receiver system is. And we're still working on that. And there's lots of trigger routines, as I said before, that we can hopefully use to dig signals out with using their unique properties. But the left side here is the events per energy bin per day. So you can see that at about between 10 to the 17 and 10 to the 17.5, we expect to see anywhere from 1 event every 10 days to almost an event per day at that energy. And if you integrate these, so basically if you integrate to the right of all these energies and then integrate over a full season, which is about 150 days in Antarctica, we can expect to see about 100 events above 10 to the 17 electron volts in our data. And so this really should allow us to test these trigger routines in preparation for the next step. And the last thing I want to mention when talking about this is that it's non-trivial to detect radio signals, not just radar, but radio signals in the ice. So there are several experiments that are doing this, and there's lots of current work in trying to study ice properties. So for a transmitter one meter below the surface, here's a couple figures that I want to point your attention to. So on the top, what we have is a transmitter right where my mouse is. So it's 1 meter below the surface, and it's just a dipole, so it's broadcasting. And because I mentioned that the index of refraction changes as a function of depth, you see that these radio waves bend, and they bend down. And what that means is if you put your receiver over here where my mouse is, hopefully you can see this, maybe at 80 meters and just at the surface, it won't see any radio, okay, in a perfect world, if you imagine that the ice is perfectly uniform. Turns out that if you introduce some slight uniformities, some slight anisotropies, there you still see this ray bending, but occasionally you'll get this strange waveguide behavior, and radio waves will get trapped, in certain pockets. And what this tells us is that this propagation is non-trivial, and we're really going to need to study it in advance of getting our detector in the ice, because it really will affect how we reconstruct our signals. And so this is ongoing work that lots of groups are working on. And for some details, I can point you to this paper here. We currently have some hardware work in progress for RET-CR. We're looking to deploy in a few years, a couple years. And we have one of the surface systems. There was this sort of Herculean effort that went on with some folks at VUB to try to get a surface system set up and taking data in the middle of the pandemic. This was last winter. And these have been set up and they're taking data. And basically, we're going to use this test setup on the roof to test our reconstruction using the surface system. So, we have a cosmic ray that's coming in. It triggers the surface system. We want to know where it is and what its energy is so that we can try to reconstruct it using radar also and test how well we can do that. And here at OSU, we've been doing some trigger development using some state-of-the-art technology that we're really excited to have our hands on. So that's RET-CR. And now I'll just, and really briefly, I think I'm going to end up a little bit early here. I'm going to briefly talk about the next step. So what happens after RET-CR should our signal be what we expect? So if we want to detect a neutrino, we want to go places where other things aren't. So this is why IceCube and Baikal neutrino telescope and Antares and all these optical detectors are very, very deep under ice or water. And that's to eliminate backgrounds so that if you see something coming from a particular direction, say through the Earth, it can't really be anything except something that can go through the Earth, which is a neutrino or some wacky BSM thing, but probably a neutrino. So the idea for the radar echo telescope for neutrinos is to put a station about 1.5 kilometers below the ice surface of a polar ice sheet. So the layout is kind of shown here. So this red guy is a transmitter. And for the sensitivity plot that I'm going to show you on the next slide, one station is this. It's a 40 kilowatt transmitter. So that's the same power as the telescope array experiment that I talked about earlier, telescope array radar experiment that I talked about earlier. So it's a known quantity and it's something we think we can do. 40 kilowatt transmitter surrounded by 27 receivers. And those 27 receivers are on 200 meters by 20 meters. This is a sort of a preliminary layout. We're actually thinking that we can actually stretch this out much, much longer. But these would be separated by a kilometer or a couple of kilometers. But this would be one station. And our sensitivity studies are still underway. So we have a publication that's in preparation. But preliminarily, I can show you the sensitivity curve. So this is similar to a plot I showed before of flux. So this is flux on the y-axis. And the x-axis is energy in electron volts. And this sort of gray mountain is one model for neutrino flux. And then these curves are all sorts of different experiments. So the actual points here are data from IceCube. So these are the neutrinos that have been detected to date. And then these are all of the limits that have been placed by various experiments or the sensitivity curves limits that have been placed by various experiments. And for 5 years with one station of radar echo telescope, we can actually cut into some of these flux models. And so that means that we expect to have some event rate. With 10 such stations, we have quite good sensitivity to neutrinos with energies beyond the reach of optical detectors, which is about where IceCube cuts off here. And what's interesting about this is that we do this with a relatively small number of stations compared to some other proposed systems. And of course, this is a projection, but we think that we can do this because we're still looking into optimizing this stuff. We can look at different transmitter and receiver configurations. One thing that we're really looking into is what kind of modulation we can put on our transmitted signal in order to increase our chances of receiving a scatter. So if we modulate our transmitter signal with some encoded modulation, it's easier to pull that out of noise than it is what we did at T576, for example, which was where we were just broadcasting monochromatic radio, so just continuous wave radio. So there's lots of things that we're working on right now to try to optimize this stuff, and it's sort of going on in tandem with our development of RET-CR. So the big picture, I hope, is that radar is the technology that can sort of fill in this gap in detector strategy and work sort of alongside these other methods, like the optical methods at lower energies and Ascarian and all sorts of other detection strategies at higher energies towards this comprehensive and complementary UHE neutrino detection program. So I'm a bit early, but that's all I had. That's all I have to present to you today. So thanks a lot, and I'll take questions.
Yeah, thanks, Steven, for a nice talk. Are there any questions from people in Zoom or people in the room?
Just go around.
Yeah. Sure. Thank you, Steven. This is a really interesting talk. I was wondering, you mentioned that you have an antenna array vertically in the ice. I was wondering, why is it vertical rather than horizontal if your events are happening close to the surface of ice?
That's a great question. There's a couple of reasons, and they're mostly practical. So it's hard to dig holes in the ice in Antarctica. And so if we dig one hole that's this big around, we can fit vertically polarized dipole antennas down that hole and phase them, instead of a single large high gain antenna that would do largely the same thing, but would have to live in a much larger hole. So that's one reason. The other reason, let me go back to, sorry for flashing slides here. So I'll point your attention to this down here. So this is the beam pattern from a vertical dipole array. And when you have vertical dipoles, they have perfect azimuthal symmetry. Okay, so they have perfect symmetry in the azimuth. So right now we're looking sort of at the side. Ice surfaces here, we're looking from the side. And they have perfect azimuthal symmetry in every direction. So when we look at the top view, which is shown up here, that means that we're illuminating this whole volume just beneath the surface with like a thin pancake of radiation. So having this azimuthal symmetry of this vertical antenna actually lets us illuminate just beneath the surface with this azimuthal symmetry. And that maximizes essentially the area from which we can expect to scatter.
All right, that makes sense. Thank you.
Sure.
Yeah, thanks, Steven. So my question is, in the test that you did at SLAC, I noticed that the frequencies that you were working with were at roughly 1 gigahertz. Is that correct?
Yeah, that's right.
And then the ones in ice for RET-CRs looks like they're at 0.1 gigahertz. Is that correct?
Correct.
What is the reason for?
Yeah, so excellent question. So this is, there's a twofold answer to this. The first one is for T576. So I told you that we did 2 runs And as Jorge can remember, the first run that we did, we saw a hint of a signal, but we were actually running at lower frequencies. We were running at like hundreds of megahertz. And that's actually because we were limited by the frequency range of our power amp. And we thought that those lower frequencies would be better, but it turns out that it's so radio noisy. Like if you were to ask me what is the worst possible place to do a radio experiment, I would tell you end station A at SLAC, because the radio environment in there is awful. So the backgrounds were really, really high, and it turned out that those backgrounds kind of fell off in terms of amplitude around a gigahertz or so. So the second time we went back, we decided to use higher frequencies, even though they were slightly less optimal for the scattering problem, just to avoid our backgrounds. So that's why we did that at SLAC. The reason we're looking at about 100 megahertz in the ice is because it turns out that there's this interplay that I mentioned between the collision frequency, your interrogating frequency, the density of the ionization, and one thing that I didn't mention is diffraction, so the actual physical size of the scattering object. And so we've run simulations, and it turns out that our most efficient scattering happens at about 100 megahertz. However, the temperature, the radio temperature of the sky is quite loud at 100 megahertz. So like there's radio noise that comes from the galaxy, the galactic background, it's quite high. And it falls pretty steeply. So we're actually looking, in order to get above that, we're looking to try to get around 200, 250 megahertz is kind of where we're looking for RET-CR. And it's sort of this interplay of several different quantities that sort of selects that. It would be really nice if we could run it like 80 megahertz, because that's FM radio, and there's tons of technology for FM radio amps, but it's not quite optimal from a noise standpoint. So we probably can't do that.
Sounds good. Thank you.
Sure.
Any other questions?
I have a question, but if there's somebody on Zoom has a question.
Somebody in Zoom have any questions? I don't think so. Yeah, you should raise your hand on Zoom if you have any questions, but yeah, I think you can go ahead.
So kind of two questions came up. One was just my own naive question of why doesn't water work? As
Yeah, so not naive at all. It turns out that water ice and liquid water have completely different radio properties. So hundreds of megahertz radio waves don't transmit through water at all, but they transmit perfectly through ice.
at the surface?
Sorry?
At the surface? I mean, it's just you're saying that it just won't work with water. Okay.
Yeah, it just, they attenuate really quickly. So submarines, the only way that they can actually communicate with the surface via radio is at ultra low frequencies. So wavelengths that are like hundreds of meters long, they actually trail an antenna behind the submarine if they want to broadcast radio waves, because those are the only waves that can actually propagate through water. Microwave and higher frequency radiation just doesn't propagate through liquid water.
Just heat up water. That's how microwaves function.
Okay.
Yeah.
So another question is, how pure does the ice have to be for this to work?
That's a great question. So it's something that the optical instruments struggle with. So as you know, light moves quite well through water. That's why our eyes developed. That visible light moves through water unimpeded. Actually, if you look at the absorption spectrum of water, it's like there's this huge, there's this perfect window for visible light. So experiments for optical that operate in water have an easier time than IceCube, which operates in ice, because of exactly what you said. It's not perfectly clear. There's stuff that scatters light. It turns out that for radio, the size of the impurity, so the size of the cloudiness, has to be commensurate with your wavelength in order for it to do anything. So tiny impurities in ice on the level of things that would mess with an optical signal do nothing for radio waves. You just go right through it. But large fluctuations in density, for example, can produce weird effects like I was kind of talking about. Sorry, I'm clicking through. Like I was talking about here. So it's not necessarily a clarity of the ice. It kind of is a clarity of the ice. It's like a radio clarity of the ice, that different length scales of perturbations and density and things like that can actually produce weird propagation effects. But those have to be
Worried
on the
about-
order of centimeters.
more about- I'm more worried about metal impurities or, dirt and dust. Whether that-
Yeah, that's super interesting. There are dust layers in the ice from like volcanic explosions and things like that over the eons. But again, it would have to be fairly dense in order for it to significantly affect, meter wavelength radio. I mean, you can use your cell phone in an elevator. Like there is a decent amount of propagation through obstacles at meter wavelengths, tens of centimeters to meter wavelengths. And so it would have to be a pretty thick layer of metal. They did get a really horrifying thing happen a few months ago in Greenland. I don't know if you read about this. It made the news. It rained on the high Greenland ice sheet for the first time in recorded history, which means that forever now there's going to be an ice layer at this place in Greenland. And that's really troubling for radar, because if there's an ice layer, that has a totally different index of refraction than snow, for example. So you would get a reflection off of that. So things like that we really need to study before we really can understand the ice that we're in.
I actually have a question, Steven. So when I left Ohio State, I don't recall if you already had a place that you all chose to deploy the experiment. And I'm thinking, like you have all these, you have 40K transmitting power, and 40 kilowatts transmitting power. And then you also have the South Pole telescope, you have other radio experiments in the South Pole. So what are they going to send you to?
Right, so that's a great question. The way that I dealt with this was by deciding to go and play in my own corner. So there are very sensitive radio instruments at the South Pole that would probably not be super thrilled by me saying, hey guys, I want to blast this radio at your CMB experiment. So we're going to go to Taylor Dome, Antarctica, which is a high elevation ice sheet about 100 kilometers from, or ice dome, about 100 kilometers from McMurdo, which is the main US base in Antarctica. And it's, there are other things running there, but no radio instruments, at least, things change down there pretty regularly, but at last check. And that's where we're going to put RET-CR. So we're going to test somewhere where it doesn't matter. Then if this works and we, it would be great to be co-located with an optical instrument, for example, we'll figure it out. There's ways to broadcast radio in particular directions and shield it and do all sorts of stuff that we can deal with being near a very sensitive experiment without interfering with them. It'll just take a little bit of engineering. But I've decided to kick that down. Sorry?
Will that melt ice? Is that enough power to melt ice?
Yeah, probably. So for RET-CR, probably not. Each antenna would have about a 20-watt transmitter, and the ohmic losses aren't really that high. But at 40 kilowatts, we'd probably need to waterproof the actual feed point, because there would be enough heat in terms of ohmic losses to probably melt the ice in the vicinity. But you're talking a fairly small region.
Okay. Great. Are there any other questions? Oh, sorry, go ahead.
So I was wondering, when you have to study the ice properties, which you have up on the slide, do you have to study them where you're going to have your experiment, right? Because it's local differences, right, that matter? Okay.
Absolutely. Yeah, absolutely. It's a great question. So the ice properties are a function of density and precipitation history, and that varies all over the continent. Luckily, this isn't just interesting for us, it's super interesting for glaciologists who have been studying this for a long, long time. So there's lots of ground penetrating radar data where they fly an airplane or drag it on a sled over the ice and just shoot radio waves down and see what comes back. And so in a lot of places, this is fairly well mapped. So at the South Pole is one of them. Taylor Dome is another one. That's why we're kind of interested in going there, because there is at least some data on it. But it remains to be seen how fine we actually need to understand the ice locally in order to not have a problem. But that's one of the things that we hope to learn with RET-CR.
One more question. When you showed your plots of event rate, the cosmic rays, I was just wondering, what is the main limiting factor on those?
So there's two. One is the flux. So the flux of the incident cosmic rays, which falls off with energy. And it turns out that the flux is about 1, like 2 or 3 actually, in our sensitive area per day. So that's just the known flux at the surface. The limiting factor then is just how much of the primary energy hits the ice. So for a vertical shower, you get a lot. As the zenith angle increases and the cascade in the air gets longer and longer, less energy hits the surface, and therefore less energy goes into the in-ice cascade, and therefore it's harder to detect with radar. So we're more efficient at detecting higher energy things, but there's a lower flux, and that interplay is what gives you our event rate. But we're pretty excited about the prospect of seeing about 1 thing per day, because that should give us enough statistics to really test our trigger.
Yeah.
Actually, can I ask a follow-up question to that discussion?
Please.
So you mentioned you expect to see 1 event per day. And given the SNR that you showed here, what kind of background do you expect?
So you mean radio background?
No, background from your noise. So noise that you could misinterpret as a signal.
Right. So I think this is actually a huge concern for, well, not huge. This is a larger concern for neutrino experiments. So like I also work on the Anita/Pueo experiments, and they have radio backgrounds that can trip the trigger or can mimic a signal, for example. What's cool about RET-CR is that we don't actually have to trigger on the radio itself. We have that surface component. And so we're actually triggered only when we know there's a cosmic ray there, because nothing else produces charged particles that are separated over, hundreds of meters. Only a cosmic ray will do that. So for this, we're kind of cheating in that we know there's something there when we're looking for it. But dealing with thermal backgrounds, as it's called for radio signals, is going to be a concern that we'll need to address with RET-N, the neutrino experiment, eventually.
Sounds good, thanks.
Thanks.
All right, sounds good. Last call for questions. If not, then thanks again, Stephen. This was a great talk. Yeah.
Thank you. Thanks very much.